Hello, here we go, another presentation on physics, a quality one here on comparing gravitational and electrostatic identities. So we're going to compare key identities here. Many textbooks cover these topics separately. However, from my experience, it can be easier to understand these topics by completing a table in the following order. These identities can then be compared and contrasted. If these are completed in the order of force, field, potential energy and potential, then the order drops out in terms of vector, vector, scalar and scalar respectively. Then the units can be discussed in order of Newton, Newton per kilogram, joule, which is a Newton times a meter, and joule per kilogram for gravitational force, field, potential energy and potential. This can then be carried out with the same order of units, Newton, Newton per coulomb, a joule, which is a Newton times a meter, and joule per coulomb for electrostatic force, field, potential energy and potential. So the very first table, we have gravitational as a heading here. We have units, vector or scalar, the equation, and the constant here is the gravitational constant big G, 6.673 times 10 to the minus 11 Newton meter squared per kilogram squared. And the vertical, we have force, field, potential energy, potential. And the units are Newton, Newton per kilogram, a joule, which is a Newton times a meter, and a joule per kilogram. The vector scalar drops out, vector, vector, scalar, scalar, in that order. The very first equation is a vector form, so you have F with the vector notation above it. On the right hand side you have the unit vector r hat. It's minus because gravity is always attractive. Big G is the gravitational constant multiplied by the product of the two masses, m1 times m2, divided by the square of the distance between them, which is r squared. The next one is a field, which is a Newton per kilogram. So take this expression for force and you divide it by mass, because that's kilograms of mass. So one of these masses drops off and you end up with gm over r squared. Minus sign still there, attractive, and the r hat for the unit vector. For energy, potential energy, we have a Newton times a meter. So you take the expression here, g m1 m2 over r squared. You multiply it by a distance, which is m here, not to be confused with mass. That is a meter. So r is a unit here for distance. And then it becomes g m1 m2 over r. Notice one of the r's of the r squared has dropped off, and there's no vector notation here or here. It's purely a scalar, a value. And then potential is a joule per kilogram. So take the expression for energy here, divide it by kilogram, which is the mass, of course. So this one of the m's drops off, and you just end up with gm over r. Similarly, for electrostatics, the title now is electrostatic. We have units, vector or scalar, the equation, and here we have the constant, which is 1 over 4 pi epsilon naught, which is 8.988 times 10 to the 9 Newton meter squared per coulomb squared. This is normally rounded up to 9.0. So you have 9 times 10 to the 9, a nice easy number to remember. Again, the same order, force, field, potential energy and potential. The units drop out as being Newton, Newton per coulomb, a joule, which is a Newton times a meter, and a joule per coulomb. Again, vector, vector, scalar, scalar. The very first equation here, unit vector, has a unit vector here and has a force here, plus or minus now, because they can be attractive or repulsive. You have the constant k here, multiplied by the product of the two charges, q1 and q2, divided by the square of the distance between them, kq1 q2 over r squared. The electric field is a Newton per coulomb, so we take the field here and divide it by one of the charges, q. Again, it's plus or minus kq, so one of the charges drops off. You have kq over r squared, and it's a vector notation in the r hat direction. Energy is force times distance. Again, careful, that is m for distance here in the units. When it comes to equation, you've got r is the distance. So you're multiplying force, expression for force here, by distance, F times r. So the r squared reduces to an r. So you now have kq1 q2 over r. Again, no plus or minus, it's purely a scalar, therefore you have no unit vector notation. And then finally for potential we have a joule per coulomb. So you take the expression here, and this is quite a common one for electrostatics anyway. Voltage is energy per unit charge. So you take the energy here, kq1 q2 over r, and you just divide by a q. So one of the q's drops off, kq over r. Again, it's a scalar, no vector notation. And finally, to summarize it all, we have on one page the difference, compare and contrast gravitational with electrostatics. You have the constant here, Newton meter squared per kilogram squared. Here we have Newton meter squared per coulomb squared. This is a very small number, 10 to the minus 11. And this is a very large number, 10 to the 9. There'll be a presentation on showing an example using this and compare and contrast. The force here, the gravitational force here is minus g m1 m2 over r squared. Here is plus or minus kq1 q2 over r squared in the r hat direction. The field is either Newton per kilogram or Newton per coulomb. Newton per kilogram, Newton per coulomb. G is minus F upon m, which becomes minus gm over r squared in the r hat. E is plus or minus F over Q, which plus or minus kq over r squared r hat. So you can see, compare and contrast. Potential energy is joule, which is Newton times a meter, and you have E, which is F times R, which is G m1 m2 over R. Again, we're now into scalars. And the electrostatics is F times R, which is kq1 q2 over R. You can compare and contrast. And the potential, which is a joule per kilogram, here is Gm over R, and here the voltage is kq over R. And that finishes the presentation. A few minutes talking through, I think, one of the most confusing topics in physics, where it's often derived over many pages and now shown in isolation. I think to summarize them together on one page, to look at compare and contrast with vector notation, with scalars, and also particularly with units, a unit approach to deriving these has been extremely helpful in my teaching and in student learning. I hope you enjoy it. Please, any comments, any likes, please, in the box below. Thank you.